into 10 power minus 27 kgs on the simplification of the powers 1.46 nanometers. Nearly, if I call this 735 divided by 3, so the answer is I am just equating energy to electron volts, de Broglie wavelength in terms of kinetic energy of electrons. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram, Pre-University, Mysuru. In my today's session on the problems of dual nature, I will be working out a few numericals from the NCERT textbook. Expect that you have gone through the sessions, you have practiced the problems and come prepared for today's class. The first one. The problem says I have to find the energy of a neutron. The energy of a neutron having de Broglie wavelength. Now, de Broglie wavelength is given, which is 10 power minus 14 meter, given the rest mass of neutron is 1.67 into 10 power minus 27 kgs. ಏನನ್ನು ಕಂಡುಹಿಡಿತಿದ್ದೀವಿ ಇಲ್ಲಿ? You are asked to find the energy of the neutron having de Broglie wavelength 10 power minus 14 meter. See, the onset, I know de Broglie wavelength is 10 power minus 14 meter, which means I have to find first what? The velocity of the neutron, so that it becomes helpful for me to calculate the energy. Fine. So I go to the basic expression for de Broglie wavelength, where I know lambda is h divided by mv. De Broglie wavelength is given. H and m are constants. So, I'll calculate the velocity as h divided by lambda m, or v equals 6.625 into 10 power minus 34. How much is the de Broglie wavelength? 10 power minus 14 into 1.67 into 10 power minus 27 kgs. On simplification, velocity turns out to be meter per second. So, first part of the calculation is done. Velocity of the electron is found out, which is nearly 4 into 10 power 7 meter per second. Now I have to calculate the energy. So, do I know the expression in terms of energy? H divided by root of 2mEk, where Ek is the kinetic energy. So, from this, energy turns out to be, taking squares, lambda square into 2 times m, or on substitution, this is 6.625 into 10 power minus 34 whole square, 10 power minus 14 whole square into 2, 1.67 minus 27. Now all of you have a simple calculator. When you simplify this, the answer will be in terms of joules. You get it around 13 into, but nuclear scale energy is electron volt. Divide by the charge of the electron. So this is 8.21 MeV. So this is the energy of the electron. The next problem, students. Again, a very simple one, a direct one. Calculate the momentum of photon. I have been asked to calculate the momentum of photon of frequency 5 into 13 hertz. Planck's constant 6.6 into 10 power minus 34 joule second. C is 3 into 10 power 8 meter per second. Momentum. Momentum of what? Photon. So students, when we have mentioned the properties of a photon, we have clearly written an expression for its momentum, where we told momentum of the photon is h nu by c. You need to know this expression. Momentum is h nu divided by c. What is the rest mass of a photon? 0. What is the momentum of the photon? H nu divided by c. So substituting 6.625 minus 34 into, what is the frequency given? 5 into 10 power 13. So this is 5 into 10 power 13 hertz. Speed of light in vacuum. Nearly, if I call this 7, 35 divided by 3. So the answer is 1.1 into 10 power minus 28 kg meter minus 2. So, very simple. This is a one marker asked. So, directly you can solve using the given relation. Next one. Again a simple one. Through what potential? He is asking us potential. An electron must be accelerated. The given charge here is electron. So through what potential an electron must be accelerated so that it will have a de Broglie wavelength of 0.5 angstrom. So we are calculating the potential through which an electron is accelerated so that it has a de Broglie wavelength of 0.5 angstrom. Now, do I have any relationship between de Broglie wavelength and applied potential? Yes. So if you religiously follow, these problems are simply expressing de Broglie wavelength in different forms. De Broglie wavelength in terms of kinetic energy of electrons, de Broglie wavelength in terms of potential applied, de Broglie wavelength in terms of thermal energy. So this is very clearly equating de Broglie wavelength with the applied potential. So very clearly we know lambda is h divided by root 2m eV, where E is the charge of the particle, V is the applied potential. So I want this applied potential, which means V equals h square divided by 2me into lambda square. I am just manipulating and modifying that expression. So now this is 6.625 into 10 power minus 34 whole square divided by 2 into mass of the electron into charge of the electron into de Broglie wavelength square. So this turns out to be, on simplification, 6 into 10 power 4 volts. See again, a simple 2 marker. If I know expressions relating de Broglie wavelength with a given factor, the problem can be solved very, very easily. Next one. Again the same notion of de Broglie wavelength. But let's see what is the factor it is been related with here. Again, find the de Broglie wavelength of an neutron. Finding the de Broglie wavelength of a neutron in thermal equilibrium. The moment you say thermal equilibrium, something related to heat, with heavy water, that is moderator. Temperature of heavy water is given 27 degrees Celsius. Mass of the neutron is given. De Broglie wavelength has to be calculated. So this is a problem where de Broglie wavelength is associated with thermal energy. And therefore, de Broglie wavelength in terms of thermal energy is lambda equals H divided by KT. What is T? Temperature given. What is K? You remember? Boltzmann constant. Very good. Therefore, on substitution again, 625 minus 34 root of 3 10 power minus 27. Do you all remember the value of Boltzmann constant? Very simple. 1.38 into 10 power minus 23 into 27 degrees Celsius. 27 plus 273, 300 Kelvin. So here, again on simplification, see, I have given you the concepts. I have given you the formulas. I have shown the substitution. Children, make it a point that use your calculators and simplify. You become familiar with the steps of simplification. So here, this becomes 1.46. And on the simplification of the powers, 1.46 nanometers. See? Just equate de Broglie wavelength with whatever is given. Solution turns out to be very, very easy. The last one, students. Find the maximum frequency. Gamnaitu nodi. Understand. Maximum frequency. Not the threshold frequency. And minimum wavelength of X-rays produced by 30 kilovolt electrons. Maximum frequency and minimum wavelength of X-rays produced by 30 kilovolt electrons. So which means V is 30 kilovolts, which is 3 into 10 power 4 volts. 30 kilovolts, which is 3 into 10 power 4 volts. So first, maximum frequency New not Allah, new. How will we do this? Simple. We know H nu is E into V. So, nu is EV divided by H. E, charge of the electron. V, applied potential. H, Planck's constant. So this is equal to 7.24 into 10 power 18 hertz. Next, minimum wavelength. How will I find minimum wavelength now? For minimum wavelength, EV is hc by lambda. See, it is simple. I am just equating energy to electron volts. First in terms of frequency and then in terms of wavelength. Simple. So this lambda is hc by EV. So again on substitution, we turn out to be 0.041 nanometers. So if you see, just relations, no quantum calculations. So I worked out sufficient problems from this chapter, practice them thoroughly. As I told, the exam bells are ringing hard. In my next session, I'll come out with problems on moving charges. Until then, have a good time. Thank you.